in some class. You ready? Okay, so we had been talking about, we're now starting to talk about strength of materials, and I actually gave a little review yesterday, and I'll repeat it here. We talked about externalities and the other limiting, or the other most important factors in determining what material you're going to select for something, okay? And so that's just a review of yesterday. And then I told you that for the rest of this class, we're going to go through some different materials, metals, an example of metal, and it'll be steel because for reasons you'll see, ceramics, and we're going to do both concrete and glass. And we're not really going to do polymers because in terms of large volume, large structures, polymers are important for small components, but no one builds big, long bridges or tall buildings out of polymers because they just don't have the stiffness, the modulus. And they also don't have the strength, except in fiber form. And they are used for some large structures if we're talking about composites like fiberglass and things like that. One thing that people have done is, over the years, this is Ashby's plot that we've seen before, they define the ages of humanity by the materials they use, the Stone Age, the Bronze Age, Iron Age, the age of steel, he puts around 1900, age of polymers in 1960. Well, I'm not sure we've ever hit the age of polymers in structural materials or any other way. The age of silicon, obviously, in the information technology, and the age of, he's predicting the age of molecular engineering, which certainly there's some exciting things going on. If we look at some of the basic needs, dwellings, homes, food, shelter, and clothing, okay? Well, shelter is a pretty basic need. This is using organic materials for shelter. A log house is organic materials for shelter. And people used to build, in ancient times, some of the first shelters were just wooden things with straw and pine boughs and whatever. This happens to be, but all those have decayed and the bugs have eaten them from thousands of years ago. This happens to be a home in either Slovenia or Slovakia or somewhere in Eastern Europe. And the design is such, you have a very steep roof to help shed the rain and stuff. And then people built more durable things that weren't eaten by the bugs in 10 years and decayed out of stone, and they didn't have anything to join the stone necessarily. This is an old stone dwelling. There's actually a modern person walking by, but again, in this case, it's stacked up to keep the rain off and to be able to structurally just lay stones on top of each other. Then the Romans come along and they started building concrete, which is basically stone houses that are bonded together with mortar, and they're lasting thousands of years, okay? And now we build dwellings out of all kinds of things. This just happens to be a steel structure. In fact, my wife asked me the other day, well, why don't they make steel homes? I said, well, yeah, they don't make them, the 2x4s that go into industrial buildings, like that building right there, a commercial building, that'll have 2x4 studs made out of galvanized steel, okay? Whereas my home, I'm doing a remodeling on it right now, it's all wood. So that's partly preference of the construction technique, okay? The commercial people like to use galvanized steel, studs, and the more traditional home construction is using 2x4s. It turns out Thomas Edison started a Portland Cement Association where, and this is his patent, 1,219,000 TA Edison on the side, but the drawing is for a continuously poured concrete house. So you do one pour. You essentially bring the formwork to the site where you want to build your house, because once you cast it, you're not going to move it very easily, right? And in fact, here's a picture. He was going to cast in the shingles, and all this work is all going to be cast in place, and the fancy little filigrees and stuff, and the porch and everything. There's a model of it. And in fact, he did build one. There it is. Can you imagine a neighborhood where everyone has a home exactly the same? But it's not going to rot, okay? It's going to last forever. So that's for one of Maslow's basic needs, which is shelter for humanity, okay? But I want to talk primarily right now about steel today, which gets back to the melting of metals. It turns out, putting a little science in this course, the adiabatic flame temperature in air of a hydrocarbon, or a carbon like coal, or coke, charcoal, is going to be about 1,000 degrees C, 1,800 degrees F, okay? If it was in pure oxygen, it might be 3,000 degrees Fahrenheit, but in fact, we got all that excess nitrogen that we have to heat up along with it, so we're limited to about 1,000 degrees C. Copper melts at 1083, so we can just barely do some melting of copper with a little preheated air and stuff. It's not too bad. Steel, we can't melt, and we're going to talk about that. Cast iron melts at 1150, so you have to do some other things to help melt cast iron. And in fact, this is another view of the Saugus Iron Works, and this is an old picture of a blast furnace where people are using carbon reduction. There in the top, they're going to pour limestone, iron ore, and charcoal, and the guy will come and dump a wheelbarrow load of each one in succession, and you layer this thing up. You have a bellows over here. A lot of times it wasn't a person holding the bellows. They actually would have a paddle wheel, a water wheel that would turn a bellows so that you would have a blast of air, okay? And with the blast of air, you can pump that temperature up a little bit, plus in this confined space, if you insulate things. So here's the brickwork at Saugus. There's the thing where they bring in the wood. They built it on a hill so that they could be at different levels. And the casting floor is right down in here, which is basically just a sandy floor, okay? And they're going to cast the cast iron when they tap the furnace about once or twice a day. And typically it has to run continuously, okay? Now it turns out steel is an important material today because it's 95% of all metal produced, and we know that metals have high ductility and toughness. And steel, though, doesn't have the highest strength or the highest toughness, although it's close to it, but it has the lowest cost by far. We got super alloys that are tougher and stronger than steel, but they might cost 100 times as much or 30 times as much, okay? Steel is the low cost, and that's why we make 95% of all metal is steel. It can be made everywhere. Iron is the fourth or fifth or sixth most abundant element in the Earth's crust, so there's iron ore all over the world. There's limestone all over the world because that's just left over from the oceans, okay? And there's trees to make charcoal or dig coal out of the ground. You can't just use any coal out of the ground. You've got to use high quality, low sulfurs. Coal, because iron sulfide melts at low temperatures, and it turns out the early iron industry could not make good steel until they found a certain ore in Czechoslovakia that had high manganese in it. Turns out of all the elements in the periodic table, the only element that will tie up the sulfur impurity in the steel is manganese. Manganese sulfide melts at a higher temperature than the melting point of iron, just barely, but otherwise you end up getting liquid iron sulfide at the grain boundaries. You try to heat it up to roll it, and you're just trying to roll a Slurpee, okay? It's got a liquid grain boundary with solid grains, and it doesn't work. But steel can be made and is made in virtually any part of the world. We'll talk about that a little bit later. It's essential to industrial economy. Countries decide they have to have their own independent steel-making capacity. They can't afford to just keep buying steel from somebody else. And in fact, they all want to sell it to somebody else. And of course, the richest single market is the United States, so they all want to sell it in the United States. And generally, we've allowed people, if they can compete, to do that. And we'll talk about some of that, how we fight back on some of that. But if you're going to build bridges and buildings other than concrete and stone, you're going to have steel to build modern skyscrapers. In fact, People attribute the fact that Bethlehem Steel, or Charles Schwab, who had a fight with Andrew Carnegie and went off and started, he was running U.S. Steel for Andrew Carnegie, had a fight with him. He went off and took this little iron foundry in Bethlehem, Pennsylvania, and created Bethlehem Steel and became the second largest steel company in the world after U.S. Steel. But Charles Schwab and Bethlehem Steel learned how to roll I-beams. And people point out that's when New York City was allowed to grow up. Okay? Before that, the tallest building was probably 10 stories tall. Some people say it wasn't just that, it was also Otis of Otis Elevator, because not everybody wanted to go climb up more than 10 flights and down 10 flights to go to lunch and back. So between elevators and I-beams, the big cities, skyscrapers came into being. I made this point a number of times. I probably never made it in front of some faculty around here who were in the polymer, not polymer, but the silicon business. But I would maintain that steel is the most technologically advanced material. Okay? You know, there's a certain fraction of the industry that is devoted to research and development. And today in the United States, the steel companies don't do much research and development, but in fact, in the past they did. I mean, the Taj Mahal Research Lab in the mid-1960s was Bethlehem Steel's Homer Research Lab. That's where I went to work. It was a $600 million research lab. It cost you $3 or $4 billion to build today. And it was just a fantastic facility because the steel companies were the big fat cats in industry at the time. But we do know more scientifically about steel than we do silicon or any other material, and I would be happy to debate anybody on that. It's one of the easiest materials to fabricate. It's easy to form, it's easy to weld, easy to machine, it's easy to repair, in part because it's easy to weld. But in any case, it's just iron is a very malleable, actually has a specific meaning, but it's a very easily worked material. It has this wonderful property, which I actually did a junior paper in my humanities class on the history of the hardening of steel. You can form it in the soft shape. It has a crystal structure transformation with temperature, and that allows you to heat it up and quench it down and harden it to 5 to 10 times its original hardness. And it can be brittle, you have to learn to temper it and stuff, but that ability to form tools in the soft condition and then harden them so they don't wear out is a fantastic property. And some people say that was the second innovation of Bethlehem Steel. They came up with hot work tool steels using molybdenum and molybdenum carbides for tool steels, and that allowed a lot of the growth of the automotive industry and other things when they came up with these tool steels in the 1890s and 1910 and stuff. The Achilles heel of steel it corrodes. Now, corrosion engineers don't think that's an Achilles heel. They think it's job satisfaction. But there are estimates that out of, what are we, a $15, $16 trillion economy in the United States, and estimates are that corrosion costs us $500 million. So 2 or 3% of the GDP is lost to corrosion each year. So it's great. You got to keep making steel and replacing that stuff that corrodes away. Hydrogen damage can cause steel to fracture. We understand it, but we still let it happen all the time. Okay, I've put a number of children through college on hydrogen and steel. Okay, and it has bad low temperature toughness. We've talked about that. Okay, stop me if you have a question. The history of steel making is that because we couldn't melt it until, we'll see, Henry Bessemer came along, taught us how to melt steel at 1500 degrees centigrade. We actually made two types of steel called wrought iron and cast iron. And basically wrought iron, if you heated the steel, the iron ore, up to below 700 degrees centigrade, With charcoal, the charcoal would form carbon monoxide, and the carbon monoxide would react with the iron oxide, or the carbon would react to form carbon monoxide and iron. And you would end up with this solid sponge. It was just like a steel sponge. It had bits of charcoal, it had bits of limestone, and you would, a blacksmith would take that chunk of limestone, charcoal, and spongy wrought iron, wasn't wrought yet, and he would forge it. He'd put it in heat it up to a red heat, and he'd hammer it and weld that sponge together. And as he did it, the charcoal would burn away, oxidize away, or flake off if it was a big chunk, and the limestone would come out. But you'd end up with something that actually had quite a few limestone inclusions. But you'd end up with a wrought iron that was bendable, that was ductile, the same type of wrought iron we know today. Okay, the cast iron, if they heated it up above 750 degrees centigrade, you'd end up with 2 or 3% carbon in the steel, and you could melt it in a blast furnace with the confined, keep the heat and blast of air. That's why it's called a blast furnace. You could melt it and you could cast it, but it was too brittle to do anything mechanically, work it to shape. So you had wrought iron and cast iron, and this can actually all be explained in terms of the iron-carbon phase diagram. Have people seen this before? You know what a phase diagram is? Okay. Do you know a phase diagram? Okay. It's a lot easier when there's only 3 students in class. They've seen it before. So here's temperature versus composition, and you have this face-centered cubic phase that you have to heat it up to if you're going to harden it. And down here you have the body-centered cubic phase, and this is the wrought iron. Below 700, this is the eutectoid temperature between body-centered cubic and face-centered cubic. And that, if you're only heating this thing up to 700 or below, you're going to form wrought iron, which is very low in carbon. That's the equilibrium. So you get very low carbon. It's almost pure iron, easy to work. Can't be hardened too much, but it's relatively easy to work. If you heat it up to higher temperatures, all of a sudden you get to cast iron. You can form a liquid at this composition, and that's got over 4% carbon. And that's cast iron, easy to cast and make things out of, but somewhat brittle, and you can make pots or lumps of whatever, depending on your casting furnace. So that's the difference between cast iron and wrought iron. Did I? Oh, I did go, okay. Going back to this. So this is coming out of the blast furnace, and this is the cast iron. And you can see they would just dig a trough in the sand, this is more modern. This is an old facility, but doing more modern stuff. But they dig a trough, and then off that they would have other things. And these are called, these little castings that are just dug, troughs dug in the sand, are called pig iron. Okay? Do you know why it's called pig iron? Because these larger pieces are called sow bars. And what's a sow? It's a female pig. And these are the little piglets coming off the sow. And that's, I'm not kidding, that's where it came from, folks. That's why they call it pig iron. Okay, and the big sow bars they would make, they were heavy, hard to work, because you needed multiple people, you didn't have cranes and stuff, and they would forge those into cannons. Okay, and the little pig irons, so they could do those into other cast iron. They make them into other things, and then remelt the pig iron, and make little utensils and cups and bowls and forges and things. Anyway, so Henry Bessemer comes along around 1856, and then we enter the Iron Age. And this is actually Bessemer's first converter. He took him about 10 years to really perfect the process. There's a door down here, so you can see this is several stories tall. Okay, it's fairly large. And there's good old Henry. And we actually owe an awful lot to Henry. Basically what people did before Henry to make wrought iron, they would take cast iron and they would basically puddle it. And puddling it means they just have a shallow trough of molten cast iron, and they would blow air through it to burn off the carbon. And so they could make wrought iron, but they were making it 100 pounds at a time. Well, Henry comes along and shows them how to build a converter that will have 10 or 20 or 30 or 50 tons of cast iron in it, and he blows the oxygen in, and he gets, essentially it's puddling on a larger scale, but he gets tons of steel rather than hundreds of pounds of steel at a time. And then a guy came along to become the richest man in the world ever. Well, maybe not ever. There might be some people in ancient times. It's kind of hard to convert. But Andrew Carnegie came along, and some people, if you read Andrew Carnegie's life story, you find some people find he was a very ethical person, and other people say he kind of pulled some shady deals, okay, to get where he got. So you can say the same thing about Bill Gates or Warren Buffett or whatever you want when you get that wealthy. But he was worth about $100 billion in today's dollars, okay? He sold the steel company for U.S. Steel to J.P. Morgan for $480 million. Doesn't sound like much today, but you know, back in those days, when a day's salary could be 10 cents. Anyway, so here's Andrew, and Andrew, if you look on the web, you'll find all kinds of quotes from him. This is one that I like, where he realized that the people were more important than the factories. That's not to say he treated the people well. He treated them better than the slaves that other people were treated as, and I'm not talking about black slavery in the South. I mean, there was indentured servitude in the North, okay, which is just a different name for slavery in the North, okay? It wasn't, they didn't own them, they just possessed them, okay? Okay, what's the difference? Okay. Anyway, and he has these beautiful steel plants that would pollute all the atmosphere and everything else. But people did earn what was a living wage, particularly for immigrants at the time. Okay, and a lot of people from Czechoslovakia. It turns out an integrated steel mill, which is what we call today, the last one ever to be built by a private company was Burns Harbor, Indiana. It started in 1964 by Bethlehem Steel Corporation. It cost them about $5 billion. They were the second largest steel company in the world, and it almost bankrupted them. Okay, I went to work for them in 1974. Turns out 1973 was the most profitable year they ever had. And I try to say, I wasn't the one who made them go downhill, okay? It wasn't just me. But it was because they built Burns Harbor, and they had one of the most modern steel plants in the world. These are the blast furnaces. These little things right here, about 20 stories tall, okay? Not very big, and there's big, you know, this is Burns, there's Lake Michigan, and here's Burns. Here's where the ore and everything comes in. It was laid out in a nice logical way. And these are some of the rolling mills, okay? Still in operation today. Most steel mills last for 100 years, so far as that goes. At the time, you almost had to build 2 blast furnaces. Because when you do a blast furnace reline, which means you shut it down for about 3 months, you can't stop the whole plant and not have any hot metal for 3 months. You need 2 blast furnaces in order to be able to shut one down and keep the other one running. You have a real problem if you're one on a scheduled shutdown, the other one for some reason goes on an unscheduled shutdown. But typically, one blast furnace will turn out about 10,000 tons of cast iron a day, and that works out to about 5 million tons a year. So you could only, the conventional wisdom was you could only build steel plants in kind of 5 million ton per year lumps. Okay, we're going to get to how that changed. But it turns out the cast iron cost you about $190 a ton for hot metal in the mid-70s. Still costs about that. The price hasn't gone up in spite of inflation because they've gotten more energy efficient and whatnot. But keep that number of $180 a ton for the cast iron, the hot cast iron in your mind. The blast furnace, huh?
I have a quick question. So,
yeah.
On some of these big construction sites, they have this Buy American clause for the steel.
Yeah.
Does that mean is there other plants in the U.S., or is that basically where they're
No, there are mini mills, and we're going to go through and talk about mini mills. And yes, they do have Buy American clauses. But about 70 million tons of the 100 million tons a year we use in the United States is produced in the United States. Okay? So it's not a big deal. It just, if you're getting into specialty steels, it can be a problem. And there are lots of different steels, but it's not a big problem to buy American. It's just could be more expensive. Those types of things do make things more expensive. So here's the blast furnace, and this is a railroad car called a slag car, and this is a hot metal car where they pour the steel. This is the stockhouse, and they bring it up a conveyor to the top and drop it in the top, just like the guy with the wheelbarrow, except it's all automated on conveyors. But a person is about the size of one of these letters, and so the base of this thing is 2 or 3 stories tall. Here's your blast of air, and the air is actually preheated. And you have these huge stacks of brickwork and different valves over here. They call these the stoves. And the cold air, blue, comes in, gets heated in the old bricks. This one, the exhaust gases will come through this one and heat up the bricks. And about once or twice a day, you'll switch the air from one stove to the other, and you'll bring the cold air into the hot brick to preheat the air. And that improves the efficiency. You're using the waste gas, the heat from the waste gas. So blast furnace would make cast iron, 10,000 tons a day. And typically they'll run for 2.5 years before shutting down. Okay? And a blast furnace reline was a great thing in Bethlehem, Pennsylvania when I was there, because it was a purchase order that everybody got a new grill for the backyard made in the metal shop. Okay? They just started turning out everything because it was such a big, expensive project that all kinds of extra government jobs, they used to call them. This is an open hearth that it's kind of replaced the Bessemer converter, but basically it's just a shallow pool about 1 foot deep of steel, about half the size of a football field, okay, in terms of this whole thing. Here are your stoves, if you will. They call them checker blocks of bricks, or recuperators in this case, but it's the same thing. And you have switching valves so that you preheat one set of bricks and you extract the heat from the hot bricks on the other thing and then switch it over. And you have charging doors where you throw in the cast iron and the scrap. You can only use about 10 or 20% scrap in this process. Most of it has to be virgin cast iron. And it takes about 24 hours. You're basically puddling the iron. You're bringing air over the top, and you're burning off the coal, the carbon in the steel. It's basically the puddling process. U.S. Steel built the last open hearths in the early 70s. They were about 450-ton capacity. Huge, okay? And this whole thing, you tap this by the whole thing lifts up. So you're lifting up this 1,000-ton vessel that has 450 tons of steel in it. What replaced it, and we're going to talk productivity here, was the basic oxygen furnace. After World War II, some people in Linz, Austria said, well, first of all, remember I told you 75% of the world's capacity was in the United States, and U.S. Steel and Bethlehem had 40% of that, of the world's capacity among themselves. And they thought they were fantastic managers. Oh, they just thought they were the best in the world. And the real reason they were so good is because they had bombed out the competition, right? They hadn't done it, someone had done it for them, but in any case. Some people in Austria wanted to find some way to get into the steel business, but they didn't have $20 billion, the equivalent of $20 billion in today's dollars. And frankly, $20 billion is sort of in today's dollars, is sort of a magic number. That's the number that it takes a huge corporation to be able to invest without some help, okay? Bethlehem Steel almost went bankrupt. They were the second largest steel company in the world. If Boeing wants to design a new aircraft, we're talking $20 billion. And so when Boeing designs a 787 or a 777, it's a bet the company proposition. Intel, we want to build a new fab, it's $20 billion. And people were projecting years ago, 15 years ago, that a new fab was going to cost $30 or $40 billion, and no company in the world, not even Intel, could have afforded it. And so they were talking about how could anybody build the next generation fab. Well, people innovated and they came up with more efficient ways to do it, and that's essentially what happened in the steel industry. The Austrians came up with the basic oxygen furnace. The process for liquefying air had been developed in Germany back in World War I era, and they decided rather than burning the carbon out, they would, with air, puddling the steel to burn the carbon out with air, they'd use pure oxygen, okay? And so they blew oxygen in. This is a water-cooled copper trough. This is the same kind of size. Actually, it's about 5 or 6 stories tall. You only put a little bit of steel in the bottom because when you blow this oxygen in, liquid oxygen, it's coming out and expanding and it's supersonic, you form a froth. And you get lots of surface area with all these oxygen bubbles burning off the carbon, forming CO, and you have a huge flame shooting out of here, carbon monoxide just burning off in the air. You throw some flux and other stuff in here, and you can make 300 tons of steel in 20 minutes. Doesn't take you 24 hours to make 450 tons. You can make 300 tons in 20 minutes. And guess what? This technology was proven in the mid-60s, but U.S. Steel management, these wonderful, intelligent people, they decided to put in open hearths at the cost of about $1 billion in the early 1970s. So they built billion-dollar dinosaurs because that's what they grew up on, okay? And they weren't willing to innovate. There was once a study done that the top 20 innovations in the steel industry were all done by someone outside the steel industry. None of the big integrated steel producers did the innovation, okay? It was always someone like this little firm in Austria, or, I'll tell you some others. So, and that's one of the things that happened to the steel companies. Before we got to fancier casting, we used to have to cast ingots, and you'd have a cast iron ingot mold that might have to weigh 20 tons or 40 tons. This one's probably about a 20-tonner because you got 1, 2, 3, 4, 5. You got 10 of them on a railroad car and another 10 back here. But if you're going to cast a 300-ton heat, you're going to end up with a number of these. And you'll have a hot top here. This is the cast iron mold, which has to have a mass similar to the steel because it's got to be the heat sink, right? So you have these ingot molds. And that was ingot casting. And whether you want to talk U.S. Steel with their open hearths versus the others, it turns out in the 1960s, the Japanese and others trying to get an edge in the industry developed continuous casting. And so this is about another billion-dollar facility. So if you start thinking about building an integrated steel plant, 2 blast furnaces, $1 billion apiece. 1 continuous caster at $1 billion, okay? 1 basic open hearth at $1 billion. And you haven't even started on your rolling mills or your facility to bring in your iron ore and everything else. It's $1 billion here and $1 billion there. Soon you're talking about real money, okay? So when I said that Bethlehem Steel was the last company in the world 50 years ago to build a steel plant, that's correct. Since then, we've built plenty of steel plants in the world, but it was always a country that financed it. POSCO Steel in the 1990s became the world's largest steel company. They passed U.S. Steel in the 1990s as the world's largest steel producer, but they were funded by the government of Korea. South Korea paid for that. The world's largest steel company today is Bao Steel in China, funded by the Chinese government, okay? Now, you can say ArcelorMittal is a huge steel company, but they haven't built any new plants that I know of. They go out and buy these other plants at 10 cents on the dollar when the great managers run them into the ground, okay? So, for example, Burns Harbor, Bethlehem Steel is bankrupt, and Burns Harbor, Indiana is ArcelorMittal Steel, okay? They bought it for 10 cents on the dollar because everybody in Wall Street decided steel was a terrible material and no one had any use for steel. This shows you what people in Wall Street know. Okay, so you have a ladle that you bring the steel from the BOF, about 20 to 50 tons at a time. You drop it into a tundish, which is just a holding tank. You have a stopper rod, you bottom pour, and it comes in here. And you use the hot steel, and you have water-cooled copper molds, the blue stuff or purple, whatever the color, I'm colorblind. And it forms a solidified skin against the copper, and it's still pliable enough you can actually bend it rather than cooling it straight down. Bring it down, you can see the red as it solidifies and the yellow. And you have a torch that comes along. You can cut through 10 inches of steel with an oxygen torch like butter. And you have a slab, and it goes off to storage. Liquid metal, solid metal, and slag. Continuous casters. These will run for 2.5 years before needing to shut down. Continuously, 24/7, 365 days a year. You can't shut them down. The only problem is if you have a breakout and you try to run too fast and you break through the solid skin and all of a sudden you dump 20 or 30 tons of steel on the floor, not a good day, okay? It's about a 2-week shutdown to clean it up and get started again, okay? And at $1 million or $2 million a day, you run into real losses. So lots of things that people do to try to improve things. Any questions on, this is the basic steel making. Bethlehem Steel put in ingot casting at Burns Harbor, even though continuous casting was sort of coming along because they didn't want to take the risk. Armco Steel did the same thing. Okay, they didn't want to take the risk. Within 10 years of putting in the $1 billion facility, today's $1 billion, it was only a couple $100 million back then, okay, they had to rip it out and put in continuous caster. Why? Because the buy-to-fly ratio, if you want to use the Air Force terminology, the amount of hot metal poured, if you go back to ingot casting, the amount of hot metal poured to product shipped is about 65%. A third of it is what we call home scrap. You got to cut off the top of the ingot, remelt it, send it back through the process. Okay, just recycle it. In continuous casting, try 97%. 97% of what you pour is what you sell. Well, at that level of increased productivity, wow, okay, that is worth billions of dollars in profit. But the big integrated companies didn't think they had anyone could touch them, and they didn't worry about things.
If they have an upset, how do they then do their QA and pull the steel out before it goes to the end user?
An upset.
So let's say that
A breakout.
the composition gets slightly off.
Oh, no. They couldn't do this if they didn't have a way to control the composition and within very tight limits. They do have to change compositions, and so they may have to pour a new composition on top of an old, which means they will have some home scrap. That's where your 3% overage goes, primarily, because other than changing composition, there's not a lot of changes, okay? And you'll have, in the country, there are dozens of continuous casters, and we'll show you how some of that works. This is the schedule. I'll just pass it out. It's going to be posted on Stellar. If anyone has any changes, they need to let Jerry know, but if it's our mistake, we will correct it and find some way to switch. If it's your mistake, okay, you didn't, whatever information you gave us, you get to find someone to change with, okay? So we're flexible, and if you really have a problem, you can always videotape your own lecture and give it to me. You're going to have to watch 20 of the 35 or so presentations. You don't have to be in class. We're going to videotape them, and you can watch them just like you watch the other things, okay? Any questions on the presentations? I forgot to do that at the beginning. I was so overwhelmed with the 3 of you in class, so I just... Anyway, Yeah.
So, do you see any like problems with the way steel is produced right now, or like any like points that require innovation, like in the future?
Well, we're going to talk about the innovation. That's actually what some of the other stuff is. I mean, we had the innovation where we went from Henry Bessemer to blast furnaces are the same for the last 400 or 500 years. Okay, they're just bigger. Okay, but we're getting out of blast furnaces, and people are trying to figure out because they use coal, coke, which is environmentally, a problem. We have continuous casting, which has increased the productivity. I've got a slide on what's happened over the time, okay? And people continue to innovate in sort of amazing ways because it's a huge industry. If you take 1.6 billion tons times $400 a ton, it's a $6 trillion industry. Well, the world's gross domestic product is only about 50 trillion, okay? Well, that means that steel is about 12% of the world's. I mean, it's huge. Anyway, one technology which was innovated, the seeds of it were right in the basement of Building 8 here. It's called Argon Oxygen Decarburization, or AOD. And the professor who worked on it was John Chipman. He had a student named William Krefsky, got his PhD. He was blowing argon bubbles through a bath of steel to look at the carbon monoxide reaction at different partial pressures of carbon monoxide. Krefsky went to a small steel company, not a big integrated steel company in the United States, and they tried to use this to decarburize high-quality steel, and it's called argon oxygen decarburization, and you can get the carbon down to extremely low values, like 30 parts per million or less. In fact, you can get down to 5 parts per million with AOD. That's lower than you can get by just blowing air through. Okay, the equilibrium won't allow you to, thermodynamics won't allow you to get lower. And today it is the way all stainless steel in the world is made. Probably dropped the price of stainless steel by a factor of 3 and improve the quality by a tremendous amount. Here's an AOD vessel. There's you can get the scale of a person by the catwalk here. A lot of the super alloys, I guess that's why I put this in here, in a jet engine have to be made by AOD. This is a nickel-based superalloy metallography, and it's not just stainless steel, it's all of the aerospace alloys are made by AOD, and the basic technology was John Chipman and Krefsky, the basic science, and then perfected with a small steel company in New York State. The superalloys now actually go to VOD, vacuum oxygen decarburization. You might start with argon oxygen and then you suck a vacuum. So you put that whole vessel inside a vacuum chamber. And this is the only thing I could find. But all of your superalloys, nickel, iron, cobalt, chrome, and all these things, in a VOD, you don't have a problem of oxidizing away these very reactive things, and you can get extremely pure, extremely good quality materials. So if I want to look at the steel productivity over time, this is a Tom Eager plot that Brian put together for me. Thank you, Brian. This is on a log scale, okay, with half-decade increments. It used to be, in the days of the Saugus Iron Works, around 1600, it was about, I estimate, about 3,000 person-hours per ton. Saugus might produce a ton of blast furnace iron a day, and they would have dozens of people cutting trees and turning them into charcoal and digging iron ore and running the blast furnace. And then Bessemer came along and taught us how to melt steel. There wasn't a big improvement over time. They scaled up size. And then Carnegie came along and came up with economies of scale, and all of a sudden the steel industries were going to millions of tons per year, mostly because of the need from the railroads, okay? And then after World War II, you had the basic oxygen furnace, the continuous caster, and mini mills, which I haven't talked about. And these were all process technology. They weren't new science of steel. It's how to make it bigger and faster. and you look at the slope we're on now in terms of person hours per ton, we're down at a few minutes per person to make a ton of steel, okay? 1975, when I worked for Bethlehem Steel, it was 50% raw material and 50% labor. Back here in these days, it was all labor. Today, it's all energy and raw materials to make steel. We've gone through this tremendous transition all in the last 50 to 60 years. And tremendous, I mean, it was, when I was at Bethlehem Steel, it was just under 10 person hours per ton. Okay, it was like 6, as I remember, in 1975. And now it's at less than 0.6, a tenfold increase in like 30 or 40 years. And as a result of that, what happened? Well, it turns out the employment in the steel industry decreased dramatically. In the 1980s, the United States used 100 million tons of steel a year. We still use 100 million tons of steel a year, approximately. We employed 500,000 people in 1980 in the steel industry. By 1990, it was 250,000, but we were still producing 100 million tons. Well, what does that say about productivity? Productivity doubled in 10 years in the 1980s when Wall Street said these steel companies are dying. All they did is look at the employment figures and said, oh, you know, people are leaving the industry. Well, they're leaving the industry because productivity was going up, okay? That's not a bad thing, folks, okay? And so here's some of my quotes from productivity. From Made in America, this book that MIT put together, and I actually worked on some of that. To live well, a nation must produce well, okay, are the opening line in that textbook, or in that book, which looked at one of the 5 examples was the steel industry, and I worked on that part of it, along with Lester Thoreau and a few other people. Productivity isn't everything, but in the long run, it's nearly everything, with Paul Krugman, a Nobel laureate who did his early work at MIT, okay? And next time we'll talk about what the difference is between productivity and competitiveness, and we'll go into a mini mill that actually the mini mills are the ones who drove this. It wasn't the integrated producers. It was the mini mills where you could come in with 20 times less capital and build a steel mill that was 1/5 the size. 20-fold reduction in capital, 1/5 the size, and it was all because they learned, a couple of people in the country or the world learned, you could buy scrap for $100 a ton. It cost you $180 a ton to make cast iron in the blast furnace. That's why I want you to remember the $180 a ton. The world price of scrap steel is still about $100 a ton. You could get $100 a ton off the $400 a ton product by making it with 100% scrap. But you couldn't do that in the BOF. The BOF can't take more than 30% scrap. The basic open hearth can't take more than about 15% scrap. The electric arc furnace can take 100% scrap. Those people realized, I can buy recycled steel cheaper than going and digging iron ore out of the ground, and there's plenty of that recycled stuff. And I made that point the other day about after a while, you put enough stuff into the environment, with the environment, I mean the industrial environment, that it starts coming back as scrap, and in reprocessing the scrap is where the gold is. Okay? So, okay. Brian will tell you about glass tomorrow, and I'll be back on Thursday and Friday to finish up some of these things, so far as that.